In this video, we'll cover limits that deal with infinities. Okay, and there's a couple scenarios where we could see infinity pop up when we evaluate limits, but we'll look at the first one when we have the limit of some function where the x values are approaching positive or negative infinity. Now, what this limit will reveal to us is the end behavior of our function. So it reveals end behavior. And when we evaluate these limits, what we need to consider, and it's important enough to star, is we need to identify the terms of the function that will, for lack of a better term, dominate the function equation or expression, I'll say. Now, the next question would be, well, how do I determine which pieces will dominate the expression? And you're just going to run through this hierarchy. So this function hierarchy, and this hierarchy is dictated by the growth rates. So what functions grow the fastest in relation to the others? So the ones that grow the fastest are exponentials. So if you have an exponential in your function, that term is going to dominate the equation. Okay, so just examples of what exponentials are. We could have e to the x, 2 to the x, and so on. Okay. For the next in the hierarchy, we're going to look at power functions. So power functions are going to be variables raised to some numeric power. So we could have x squared. We could have x to the third. We could have x to the 2/3. Okay, and so on and so forth. And then lastly, the slowest of the bunch are the logarithms. And the logarithms, like ln x, will appear often, or log base b of x, so replace b with some positive number, and you'll have the logarithm example. Now we're going to leave out the trig functions, because those just oscillate between values. So we don't need to look at those. But again, when we're looking at limits at positive or negative infinity, we got to pick out which piece of the functions are going to dominate the equation. And what we also want to take note of is one of the results that could happen when we do this evaluation reveals to us an important aspect of our function's graph. And that will be the horizontal asymptote. These will occur if, when upon evaluation of the limit, as x goes to positive or negative infinity, we get some constant value. And I need you to know this definition and this notation here. So if the following occurs, upon your evaluation, you just revealed a horizontal asymptote. So we can say, if this is happening, we can say we have a horizontal asymptote at y equals c. Okay? So if the limit of the function as x goes to positive or negative infinity equals a constant, you just identified a horizontal asymptote. Now, your experience in previous like your pre-calc class, would have explained to you how to reveal horizontal asymptotes with rational functions. So let's just do a quick review of that. So, horizontal asymptotes of rationals. And then remember rationals if you forget. So rational is just equal to a polynomial divided by a polynomial. Okay? So horizontal asymptotes with rationals, what you're going to do Step one, identify the terms of highest degree in the numerator and denominator. Once you have done that, you're going to compare to reveal the limit. Or, sorry, not the limit, the horizontal asymptote. And to do that, we'll say if the degree of the numerator is greater than that of the denominator, then there is no horizontal asymptote for that graph. If the numerator is less than that of the denominator, there is a horizontal asymptote at y equals 0. And if the degree of the numerator and denominator are equal, there is a horizontal asymptote at y equals the ratio of the coefficient of the leading term in the numerator and the denominator. So it's going to be equal to coefficient of leading term divided by coefficient of leading term. So we can just run through some quick examples to refresh your memory on that. So let's just say, example, let's say we have the limit of x squared plus 4 as x approaches infinity over x minus 2. So we have a rational function here, polynomial divided by polynomial. We identify the leading term in the numerator is x squared, in the denominator it's x. The numerator has a higher degree than the denominator. Therefore, we don't have a horizontal asymptote. What the value of that limit is, we'll look at in a second when we discuss indeterminate forms. The second, let's say we have the limit as x approaches infinity. Actually, let's do negative infinity just to throw a wrinkle in. Let's say we have x cubed minus 5x over 6 plus 2x to the 4th. So on the top, the leading term is x cubed. On the bottom, it's 2x to the 4th. So when we evaluate for this horizontal asymptote, the numerator is now smaller than the denominator, and therefore we have a horizontal asymptote at y equals 0. And then lastly, what happens if the ratios, or not the ratio, but rather the terms are equal in degree. So the leading term in the numerator is x cubed, in the bottom it's x cubed. So the x cubes, in this case, as x approaches infinity, are actually growing at the same rate, and therefore they essentially cancel each other out for their rate of growth. So all that's left to determine where this function's going towards as x goes to positive infinity is the ratio of the coefficients of those terms. So we have 1 over 3, so we have a horizontal asymptote at 1/3. Okay, so that was just a quick refresher on that. We'll now look at if we approach a positive, or sorry, not positive, if we just approach some constant and the limit is positive or negative infinity. So we'll kind of reverse that. In previous videos, we strictly looked at limits that approach constant values. So in the previous slide, we saw what happens if x approaches positive and negative infinity. But now let's jump back and say, well, what happens if we have a limit of a function and x is approaching a constant, but this time, rather than approaching a constant value as well, this function is heading towards positive or negative infinity. What does that reveal? Well, if in the case we have We're going to break this apart. Well, actually, what it reveals is vertical asymptotes. But to reveal a vertical asymptote, all you need to do is actually look at a one-sided limit. So we don't need the full two-sided limit. So vertical asymptotes will occur if we have the following. So if we have the limit of f of x as x approaches a from the right, if that equals plus or minus infinity, we just revealed a vertical asymptote. Or, so it doesn't have to be both, one or the other, the limit of f of x as x approaches a from the left equals plus or minus infinity. So I need you to recognize this definition as well. So if you see that when we evaluate a limit, we're getting the following result, where we approach a constant and the limit is going towards positive or negative infinity, we are now revealing a vertical asymptote. And vertical asymptotes were also, again, they were discussed in pre-calc. So as a quick refresher on how to identify vertical asymptotes with rational functions. What you do is set the denominator equal to 0 after cancellations. Then solve to reveal vertical asymptote. So example, I'll do it in blue. Maybe we have some expression like x minus 3 over x squared minus 9. So we have to set this equal to 0 after cancellations. Okay, so we can see there's going to be a cancellation because if I factor the denominator, I can cancel it with that x minus 3, and I'll have 1 over x plus 3. Then I set this denominator equal to 0, and I solve, and I'll get a vertical asymptote at x equals negative 3. And the vertical asymptote equation is a vertical line, so x equals is the correct notation, and that is how you do that. We don't want to do it before cancellations because if you recall, cancellations reveal removable discontinuities or holes. And in a later video, we will discuss discontinuities in further detail. But for now, just recall that we want to make sure that when we're looking for vertical asymptotes, we're setting the denominator equal to 0 after cancellations have been made. So we've seen how to identify horizontal asymptotes and vertical asymptotes based on the results of certain limits. So now, when we're evaluating limits, we need to be aware of these indeterminate forms that could pop up when we're dealing with infinities. Or even if we're evaluating at some constant and we get that 0 over 0. So we saw that in a previous video, and I told you how to deal with that. Again, we're just going to do some more work and reevaluate. So look for some cancellations. But the others I want to take a closer look at so you know how to deal with them as well. There are more indeterminate forms than what I have listed here, but these are the primary ones that you will come across. So first, let's take a look at this infinity over infinity and how you deal with that. So I'll write an example here. Let's say we have let's make that thinner. Let's say we have to evaluate the limit of e to the x over x as x approaches infinity. Now, even though infinity is not a constant, sometimes I myself like to still think of the direct substitution approach to figure out where these things are headed. So if I were to like plug in infinity, even though that's not literally what's happening, to the numerator, so e to a number that continues to get larger and larger and larger is going to give me numbers that keep getting larger and larger and larger. So the overall value of the numerator is going towards infinity. And in the denominator, it's just x. So as x heads towards infinity, that value in the denominator is also headed towards infinity. So we have this ratio of infinity over infinity. And a common mistake that's made is you see this ratio, it's like, oh, I have the same thing at the top and the bottom, so this must be equal to 1. Well, it's not, okay? Because, again, we're not taking these indeterminate forms as literal arithmetic problems. It's not literally 0 divided by 0 or 0 times infinity. Remember, when we're dealing with limits, we're asking ourselves where are the functions approaching. So it's as we approach infinity, in the ratio, we have to make an assessment on, is the numerator growing faster than the denominator? Is that happening in the opposite fashion, where the denominator is growing faster than the numerator? Are they growing at the same rate? And to determine that, we're going to use that function hierarchy that I mentioned earlier in the video. We see that we have an exponential in the numerator, and then we have a power function in the denominator. And I said exponentials grow faster than power functions. Therefore, even though both the numerator and denominator are going towards infinity, the numerator is growing faster than the denominator. So what's going to happen, and this isn't the literal rate of growth, but just to give you an idea of what the separation that's occurring. Let's say I have 10 over 1, and the numerators are growing by a factor of 10. So the next numerator is 100, then 1,000, then 10,000. And the denominators are just growing by, they're just going up by 1. So 2, 3, 4. So you can see that as we progress in each direction, these are both going towards positive infinity, but the overall value of the ratio is increasing. So the overall value is heading towards infinity, even though, again, you might make the mistake of thinking, oh, it's infinity over infinity, so it should just be 1. But again, you have to consider the rate of growth. So when exponentials grow faster than power functions, we know that the overall value is going towards infinity. Now, let's say this was reversed. What if we had x over e to the x? And we had to take that limit. Well, now the exponential's in the denominator. So now the bottom's growing faster. So even though we have infinity over infinity, we can't yet determine that. We have to think a little bit harder and make an analysis on the rates of growth of each portion. Because the denominator is growing faster, imagine if I flipped all of these ratios. Where would the value of those ratios be heading? Well, they're getting smaller and smaller and smaller and actually approaching 0. That's why it's important to know that function hierarchy and what grows faster than others, so that you can make the correct assessment on where the limit is actually going. Now if we take a look at this product indeterminate form, again, you might think, oh, I'm seeing that and I see 0 times infinity, and anything times 0 is just 0. But again, this isn't like a literal arithmetic problem. We're thinking as we approach 0 and as we approach infinity, where is the overall value headed? And maybe the best way to illustrate how this happens is that we can use the exact same problem as before. We're just going to write it a little differently. So let's say we have the example. We'll say limit as x approaches infinity. And then before we had e to the x over x, but what if the problem said e to the x times 1 over x? Now you could reformat this so that you do get a ratio, but let's say you didn't recognize that. And you do that direct substitution approach, and you say, well, e raised to a number that continues to grow large is going to be infinity, and 1 over a number that keeps getting larger and larger and larger will tend towards 0. So let's actually make a note of that. I think that's worthwhile to write down. So let's say we have the limit as x approaches infinity of 1 over x, this equals 0. And we can just make a more general case. We can say the limit as x approaches infinity of like a, so some constant a over x to the b equals 0. Okay? Where b is a positive number. Okay, so we can put that in our notes somewhere. I think that's a useful thing to recognize, that like when I have a number or a constant over a number that continues to grow larger and larger and larger, the overall value of that ratio goes to 0. So I would take note of that. Now, let's get back to our problem. So we see we have this infinity times 0 scenario. And again, I don't want you to make the mistake of thinking this is a literal arithmetic problem where we're doing 0 times infinity. What we have to assess is when I look at my function, I recognize that this exponential piece is actually growing faster than this power function piece. So the overall value is actually going to go towards infinity faster than this goes towards 0. Again, it doesn't equal 0, it's going towards 0. So the overall value goes to infinity. Okay, so who wins this race as we go towards a certain value? Okay. So that would be a product scenario. And then lastly, let's look at the difference. So example, let's say we have the limit as x approaches infinity. Actually, let's do negative infinity for a change of pace of, actually no, we'll just do positive infinity because I want to throw a logarithm in there. So let's do natural log x minus, we'll say x squared. Okay, so upon direct substitution, as x goes to infinity, the natural log of x also goes to infinity. As x squared goes to infinity, or sorry, as x goes to infinity, x squared will go to infinity. So we have infinity minus infinity, and we may want to say, based on our intuition, that, oh, I'm doing infinity minus infinity, that must equal 0. Well, again, no, we have to consider rate of growth. Logarithms grow the slowest out of our 3 function types that we mentioned before. So this x squared is going towards infinity faster than the logarithm is. So the overall value, we're taking away numbers quicker than they're being added in by that logarithm. So the overall value of this is going towards negative infinity because that x squared is growing faster. So again, imagine just quick numbers. This isn't the literal rates that are happening, but let's say I had 1 minus 2, and then we had 2 minus 4, and then we had 3 minus 8, and then we had 4 minus 16. You can see that the initial numbers are still going towards infinity, and the second piece of the equations, those are also going towards infinity. But the overall value is heading towards negative infinity because we're not subtracting numbers that are of the same value all the time, right? There's a rate of growth associated with these values. So this goes to -1, -2, -5, -12, and you can see that the overall value is going towards negative infinity. So that's what I mean when you have to compare rates of growth. So again, make sure you know that function hierarchy when you're assessing limits that deal with these indeterminate forms. And to close out the video, we're going to look at end behavior models. So, with complicated functions, let's see. So when we have complicated functions, we can get an understanding. So an understanding of its end behavior can be found through a simpler function that behaves the same way. Or behaves similarly, I'll say. So here's how you identify an end behavior model for a function. So to identify, determine, which I'll just write as one sentence. To identify, determine the term that dominates the function. And how are you going to do that? Well, I'm sure you guessed it. You're going to look at that function hierarchy again. A more formal definition is so to check if you actually are using the correct end behavior model, we can say g of x is the end behavior model for f of x if the limit of f of x divided by g of x as x approaches this plus or minus infinity equals 1. Okay, so that's how you can check. So let's just look at an example. Let's say we have f of x equals x to the fourth plus 2x plus 4. Now, without using the formal definition, to find the end behavior model, what I would do is just identify the term that dominates the equation, and you can probably recognize that it's going to be x to the fourth. So my end behavior model, g of x, is going to equal x to the fourth. Okay? Now to check that I'm right, again, I can use that formal definition and say, well, if I do the limit of this divided by this as x goes to plus or minus infinity, I should get 1. So what we can do is, well, what is f of x divided by g of x? So that's going to be x to the fourth over x to the fourth plus 2x over x to the fourth plus 4 over x to the fourth. Now as I take these ratios as x goes to infinity, well, these cancel out. They're growing at the same rate, so this equals 1 plus, back to our indeterminate form. This goes to infinity over infinity, but what rate grows faster? The denominator does. So the overall value is going towards 0. And same thing over here. We have constant over something that's going towards infinity or negative infinity. If it's negative infinity, the power of 4 makes it positive. So that's also going to 0. So the overall value goes to 1. So I know that that g of x serves as the correct end behavior model. And then really quickly, to make your life even easier, if we have a ratio of two functions, the end behavior model is the ratio of the term that dominates the numerator over the term that dominates the denominator. And I think that's really the thing you should take away. If you have to find an end behavior model and you have a ratio, just identify the term that dominates the numerator and divide it by the term that dominates the denominator, and that will reveal the end behavior, because all we're concerned with is what's happening as x goes to plus or minus infinity to reveal end behavior. So what goes on in the middle doesn't really mean anything to us for this type of problem. And that will be the conclusion of limits that involve infinities.